Morning, everyone. Thank you for joining my presentation seminar today. It's my first presentation, and I'm gonna introduce my recent work on efficient multimodal large models. So the title is Leo Mini, an efficient multimodal large model using conditional token reduction and MOE experts. So this paper we published on EMLP 2025, and we're still working on the follow-up works on it. Yeah, I forgot to introduce myself. I'm Yimu, and my supervisor is Professor Christoph. I'm from computer science in my PhD degree. So first, I'm gonna give you the background and a brief introduction of large model. Large models are usually trained on a very large number of text to understand and generate human language given the input text. So usually the input is text, and we're going to have a large model backbone. The backbone is usually transformer or deep learning neural networks. And usually people use autoregressive or like prediction generative methods to generate the text given the inputs. And the larger model will be expected to predict the next token given the previous input and generated text. But in this way, though it's only a simple next token generation task, but now people see large model can do a lot of tasks in the real world, such as semantic parsing and or understanding, and there's a lot of reasoning tasks large model can handle, which shows how scaling up data and scaling up model can give us very good performance in regarding the real world application tasks. Extending from large models in vision and audio and also like 3D LiDAR arrays, people are also thinking about how we can utilize larger model in those multimodal scenarios. So, but the things different from larger side is in image and video and audio and also maybe 3D with lack of a very large number of data, image only data. So to enable it with like video, image, audio understanding with limited number of training data. So people are now trying to connect other modalities with larger models to see whether larger models can understand image and provide a reasoning ability provided by learning from a large number of corpus. And surprisingly, that seems to work for now. So people use a modality encoder to encode image, video, audio, those data from other modalities besides text into a sequence of embedding. And then we usually add a modality projector to project the embedding into something that large model can understand into the longer space. And the large model will take the input of transformed image, video, audio embedding, and also the input text. The text will be representing some queries and questions from the users. And large model backbone can usually give us generated text given the video, image, and also the questions. On the other side, people are now also working on to see whether we can use larger model to do generation for other modalities as well. So in this paradigm, people are usually at output projector and then modality generator to generate image, video, given the embedding, given the representation generated by large model backbone. And some representative work will be models from Alibaba and models from Netflix. They can do generation, text generation, and image generation, video generation at the same time using only the one same large model backbone. And in a nutshell, the conclusion is a large model, multimodal large models connect multimodal data with LLM to foster the knowledge learned by large models to give us the reasoning ability, generation ability, and like real-world understanding ability instead of directly learning from limited training image and video training data. So this is the background of large model and multimodal large models. And in our case, we want to, because for now, the general image understanding multimodal large models paradigm still have a very big bottleneck on efficiency. So I reframe this paradigm into this like simple graph. So first, still we get images as input, and images are input into the vision encoder, and we get the visual tokens, which is the embedding of input image. And then the visual tokens will be put into large models with instruction as input as well. We get the final response. Okay, so usually we have the image as the input of multimodal large models, and people use vision encoder to generate the visual tokens as the embedding of input image. And we usually have a projector here, but I omitted for simplicity. Large model will take the input of visual tokens and also instructions to generate a response given the image and queries the instructions. But in this paradigm, a very big problem exists with the efficiency bottleneck, because like for visual tokens, usually they're in a very large number. Clip gives us 576 visual tokens, but usually questions are less than 100 tokens. So, and we know large model process tokens one by one. Even in the pre-filling stage, the very large number of tokens still give us very huge latency that will very high computational cost. Researchers now are working on token reduction to see whether we can reduce the number of visual tokens. They sometimes reduce the number of tokens from 500 to 100, but there's a lot of drawbacks in this problem, though they give us very like quick, short latency, improved latency, and improved efficiency. The problem of those token reduction methods is they are usually use self-attention or non-parametric methods to give weights to visual tokens, and then they select or merge tokens based on the weights, but they're usually like non-training free, and the token reduction might not be suitable for all the tasks, and which give us pretty bad performance. So overall, the advantages of token reduction methods for now, the first method is they give us very fast training and inference time, like improved performance. But they also give us very bad performance. Usually they're training free, and they usually only consider self-attention based on the visual tokens, and they do not consider textual signals. Because the input instruction, the question can also give us some guidance, like if they're asking specifically some objects in the image, we can just focus on the image to generate the answers instead of looking at the whole image. Okay, a brief review on token reduction. So usually we generate, as in the previous slide, a sequencing map or generate token importance for each tokens. Or sometimes we also do clustering to cluster similar visual tokens into one small cluster. And then we usually do like selection, like we're only selecting the top K tokens with highest importance or highest segmentation weights, or maybe we sometimes do combination in the same classes, like such as weighted average pooling, so that we can obtain a small number of visual tokens and improve the performance. But still, that give us very bad performance usually because they only consider the similarity between visual tokens. They never consider signal from the guidance from the question side. And also that kind of simple combination and section always leads to information loss on the image side. So yeah, this is the problem we investigate in this project. Next will be our research goals. So what we want to do is we want to improve the effectiveness because we still want to have like comparable reasonabilities performance regarding performance general benchmark data sets. And also we want to reduce the number of visual tokens so that we can get improved efficiency during training and inference. Next will be our proposed solutions. The first part corresponds to the performance effectiveness part. We introduce multimodal experts to maintain the overall performance. Specifically, we have multiple visual encoders incorporated in this paradigm. We use some ComNext, EVA2, Extruct, and also Dino. Not showing on this slide, but we also use Dino for getting a comprehensive visual representation from multiple visual encoders. And also we added like a LoRA mixture of LoRA experts on the large model side to improve the capacity of large model. This is for effectiveness, the performance. And also regarding the second research goal in the previous slide, we reduce the tokens with guidance from image and text at the same time to guide our token reduction. Because in the previous background token reduction, we have shown that the previous method, they only consider the signal from self-attention, usually, or silence map, and they ignore the guidance from questions and instructions to improve the performance of token reduction. Okay, the proposed overall architecture of our multimodal large model is still similarly, we have input image as the input, and then we're gonna use token reduction for efficiency here in the middle. And similarly, we have multimodal mixture of experts vision to utilize multiple vision encoders to give us a comprehensive image features so that we could maintain the performance of multimodal LLMs. Also on the top right, to fine-tune the large language models, we incorporate multimodal, like still large language model with multiple LoRA experts to improve the performance of multimodal LLM. The paradigm remains the same. We have image, text as input. We use a vision encoder to generate the image embeddings. But different from like general paradigm is we have multiple vision encoders. We have token reductions here for performance and efficiency, and also we have multimodal multimodal mixture of experts LM, like multiple LoRA in large language models to improve the performance. So next will be the details of each module in the proposed model. For multimodal mixture of experts feature part, what different from previous methods, they only used one visual encoder to generate the visual tokens. Here we use multiple visual encoders because for different visual encoders, they usually represent like the angle of different angles of understanding the world. Like SAM is trained on segmentation, a very large number of segmentation data. It usually provides us with very detailed fine-grained representation. And EVA is trained on detection. So like instead of fine-grained understanding, they usually give us a little bit more coarse-grained representation. And for ComNext, is very, very coarse-grained because the ComNext is trained on image classification task. And also ComNext is a fully convolutional neural networks. And the bias, the prior is different from SAM and EVA, which are based on transformer. And the final one is text-to-struct. It is trained on tabular data understanding. So it will just give us a different angle because it mostly work on the structural data. So this different visual encoders, instead of giving us like redundant visual features, they give us a comprehensive, like complementary to each other, so that our visual tokens can be more comprehensive, and that will give us a better understanding, visual understanding of the text. Yeah. Overall, they give us expert level visual capabilities, and they can improve the performance with acceptable computational overhead, because usually visual encoders are lightweight compared to large language model, the large language model backbone. Next will be the details of our MoM large language model. To efficiently fine-tune the model, instead of doing a full fine-tuning on larger model, we do a LoRA fine-tuning. However, we know LoRA fine-tuning, the capacity is limited. So regarding this part, we improve some new elements here. The first one is we employ a general expert here for learning general knowledge from all the training data set and like all the data. And it will be activated all the time to learn new knowledge we learn from the new training data. And also we have a group of special experts added here to learn domain-specific knowledge. We also have a router to route between them, so that different special experts can learn from different domain of knowledge. So what we expect is maybe for the first expert, they learn still like general or OCR. The second one can learn medical or health, and third one maybe learn something from autonomous driving, or maybe animals, like specific domain knowledge. And more efficiently here is our router also use text and visual instructions, the input image and input text, input question, to route between different experts, because we believe that the guidance from visual and text, the image and question, can give us better understanding of which domain knowledge will be the best for the current input. Okay, the final new things here is our token reduction module. So for each visual tokens here, we want to calculate the self-attention or cross-attention similarity, and then we can assign weights to those visual tokens to get like a small number of visual tokens. But different from previous methods, they only use self-attention. We use 4 kinds of different input source, like knowledge source, to guide us in this token reduction procedure. The first information we use is the learnable query, a general prior learned from the training data. So the query will learn a general knowledge, such as like the edge of image will be less important compared to the center of image. So they will assign higher weights to the center of image and lower weights to the edge of image. And the query can control the shape of the output. And also, because we use multiple visual experts, so for visual tokens generated by each expert, there are gonna be other visual tokens. And we also want to calculate the similarity between them and that will represent the common knowledge between different visual experts. So like if some object is highlighted by Clip, Eva, and Dino at the same time, that might be some important things that we need to focus on. And the third things we're caring about here is the text signal. So we also consider the guidance from the input question, because if the question is clearly asking some objects in the image, so we should definitely just focus on that object instead of the whole image. And the final thing, similar to the previous work, that will be the self-attention map. So we calculate the self-attention between of the original visual tokens, and we get the attention map. And finally, by summarizing the attention map from those 4 different guidance and and we get the final outputs. Yeah, I might misdelete one thing. So by this attention map, so we multiply the attention map with the original visual tokens. We get the final small number of visual tokens here, so that we can use 4 different guidance to have a small number of visual tokens for improved efficiency of our multimodal language model. And the advantage of this proposed method is we use 4 different guidance, and that will represent 4 different knowledge thoughts. They can give us different angles of understanding these visual tokens. And also it is easy to change the shape of outputs because the shape of query controls the shape of the final output on the right key. Okay, the final things I'm going to introduce for this project is the experimental results comparing with LLaVA Next. We only use 3% of visual tokens, number of visual tokens, and we only use 40% of float and 10% of GPU running time. And our model has also improved performance compared to LLaVA Next and also mini Gemini HD. So yeah, our model is on the top left, or top left is the better. So the top left is better than the bottom right part because the x-axis represents the number of visual tokens, larger is worth, and the y-axis is average performance, higher the better. So on the up left will be the best model. Our model have like in general, we use small number of visual tokens, but we have better performance compared to combining 11S mini H Gemini, but a little bit worse than Eagle X4, a model introduced by NVIDIA. Regarding the effectiveness, we also compare to, regarding the efficiency, we also compare the inference cost only compared to LLaVA Next and also Eagle X4 Plus. Compared to those models, VT here represents the number of visual tokens. We have different version of our Leo Mini. So for the one, we only use 64 visual tokens. We reduce the number of visual tokens by 97%, and we only use 40% of floats compared to LLaVA Next and still 10% of CoTR running time. And a little bit more GPU memory compared to LLaVA Next because here we use 4 vision encoders. Compared to Eagle X4 Plus, we have less GPU memory consumption here. So our next application study we did here is we want to see how is our router route between different experts. So here E0, E1, E2 represent 3 different special experts, and we can see on different data sets on test VQA and on GQA, the activation map are totally different on different on those 2 data sets. So for example, in the middle layer on test VQA, the model, for example, on the 11 layer model is more preferred to activate the first experts. But on GQA, the model preferred to activate all the experts evenly. So that represents different preference between different dataset benchmarks. Also, the next application study we did here is we want to see how many visual tokens is enough in our case. So we're doing experiments on our default setting is using 64 tokens. We also do experiments on 116 and 256 number of visual tokens. What we can see here on the average performance of several benchmark datasets. So using one visual tokens, we only get a little bit smaller drop compared to 64. But if we improve the number of tokens to 256, we only get a little bit improvements here as well. So which shows that our token reduction module is very stable and very efficient. And we also add the performance not using visual token reduction here. So the last row using 1,000 tokens represent the models without trained without using any token reduction methods. The average performance is on the 73.4 compared to our model is only, I mean, the improvements is marginal. And so which shows that still our visual token reduction method is very highly efficient. And the final application study we do here is we want to see will more training data help. Our default is our default model is trained on 600,000 untraining data, accepted data, and also we want to see if we triple the accepted data, can we have some improvements? And definitely yes, we did see some improvements here, but we also see some performance drop on MMoE perception and also GQA. So that means in general, with more training data, our model can get better performance, maybe approaching the performance of model without any token reduction methods, as shown in the previous slide. But given the computational constraints, for now our default setting is using only 600K training data. Okay, the takeaways of our paper, our project here is our Leo Mini only using 3% of visual tokens with our conditional token reduction model, but it still can keep essential, important visual information, achieving very good performance compared to previous methods. And also our mixture of multimodal experts give us improved performance. Regarding the limitation of this project, so the first limitation I observe here is Leo Mini is still employing multiple visual encoders for improving the performance, but that definitely gives us additional computational time, and also as shown in the inference cost slides, we can see that for GPU memory consumption, we use more GPU memory compared to Lava Next. So that'll be the first limitation. And the second limitation here is Leo Mini lacks of direct supervision of token reduction. The overall training loss here is still the next token generation, the text to text generation loss. That'll be the cross entropy loss regarding whether the next token generation is correct or not. So the next step, maybe we can propose a direct supervision signal for token reduction, such as using visual generating models to supervise the token reduction process. That might be better. And the final drawbacks here is our token reduction module is not training free, which means if we want to expand it to test it on more models, we need to train the models from over and again. That will be very time consuming and a heavily computational time cost. So for those three limitations here, for the first limitation, we have a follow-up project, and the paper is published on New York 2025. Our solution is, instead of using multiple vision encoders, we distill the knowledge from multiple teachers into one visual expert, so that in the training and inference time, we only need to run one vision encoders. That will improve the efficiency and will not the GPU memory consumption will be less. And for the second one is we can design a new supervision signal for token reduction module. And the final thing, limitation is we can do a training for a token reduction to see whether we can have some similar results or similar observation in this line of research. Okay, yeah, that concludes my presentation. Thank you for your time.